Hi guys, right, so in this video I'm going to be talking about the action potential, how it can be initiated, how it moves along the axon or dendron, and then finally how it gets to the other end of the neuron. Alright, what happens to the signal after it gets to the end of the neuron, that will be the subject of a different video. Okay, so let's begin then. So what we have to realize is the signal that's going to be passing along the neuron is an electrochemical one, and it's brought about by the movement of ions, all right? And the main ones that we'll be concerned with are sodium cations, i.e. positive sodium ions, and potassium cations, okay, so positive potassium ions, all right? And it's the movement of these that means, or that establishes whether the cell is at rest or if it's passing a signal along, okay? So what we'll begin with is what the cell conditions are like at rest, okay? So initially we'll be talking about the resting potential. What's happening, what's the situation along the membrane of the neuron at rest, okay? So key things that we need to know about the resting potential are, first, what's the balance of the ions? So you've got lots of sodium outside the cell, and you've got lots of potassium inside the cell, okay? And generally, the outside is said to be more positive than the inside, okay? Now, the reason for this imbalance is due to our first player, the sodium-potassium pump. It uses the energy from the breakdown of ATP to ADP plus a phosphate group, so it's using energy to move these ions against their concentration gradients, okay, as well as the electrical gradient. So the sodium-potassium pump, okay, moves, or we should say actively, or moves by active transport, actively transports 3 sodium ions out and 2 potassium in, okay? And because of this imbalance, so 2 positive charges coming in, 3 positive charges being moved out, it creates a bit of an electrical as well as a chemical gradient. The electrical gradient is because there's more positive charges outside than inside, so that's an electrical gradient. But also there's a chemical gradient because there's lots of potassium here, but not that much outside, so it's making a gradient of potassium. But there's lots of sodium out here and not that much inside, so that's the chemical gradient. And it's these 2 gradients that influence the direction that these ions are moving in, okay? So the resting potential, what we have to remember, is mainly due to the activity of the sodium-potassium pump, okay, using energy to maintain this gradient, okay? At this stage, we need to remember that sodium channels are closed. This is important because what that means is that the sodium is not allowed to come back inside, okay? And because of the electrical gradient, potassium won't move outside because outside is already more positive. So let's just put, at this stage, at the resting potential, positive and negative within the membrane, okay? positive outside, negative inside. All right, now that's the resting potential. It's around about minus 70 millivolts. Okay, so maybe we could follow the graph. Okay, so let's just say that the resting potential actually so the resting potential should be about there. So we are there at the moment. Okay, so that's 0. That's 40 there, and it's not to scale, minus 70 there. Millivolts. Can you see that? Just about. Okay, so resting potential, maintained by the sodium-potassium pump, and the sodium channels are closed, preventing sodium coming in. Due to the electrical gradient, potassium doesn't go back out. Okay, it's already so positive in out there. Sorry. Okay, so that's our resting potential. Now let's move on to what happens when we get a signal. Okay, so this neuron is going to be receiving either it's going to detect something itself, some form of energy itself, or it might get activated by a receptor cell. Okay, but in any case, what happens is that these sodium channels get opened. All right, now maybe it's some form of energy that directly leads to the opening of the sodium channels, or it might be that these sodium channels need to bind something, some kind of chemical messenger, which makes them open. In any case, sodium channels open, which is activated by some form of energy ultimately. Okay, so let's just say that the sensory part of the receptor part of this neuron is here. It's just detected some form of energy, and that energy has caused an alteration in these sodium channels, which causes them to open. So, and remember, we've got lots of sodium outside, but they were closed when the cell was at rest. However, the sensing of this energy has caused the channels to open. Okay, so sodium channels open. Right, so let's just call this stage reception. Okay, so yeah, so either chemical or some form of energy causes sodium channels to open. Okay, so some kind of stimulation, right? Stimulation. All right, so these channels open. Remember, there's already sodium outside. There's a chemical gradient. So if these channels open, sodium will come in. Okay, so sodium rush comes in down its concentration gradient. Okay. Now, the next players in this little scene are the voltage-gated sodium channels. Okay? So now this is the beginning of the action potential. All right? Action potential. Right? Now the initial entry of sodium into the cell causes a depolarization. Right? So this was polarized. The cell was positive outside, negative inside, so it was polarized. But the entry of sodium into the cells meant that it became less negative. So it was negative before, but now we've got positive ions coming into the cell, so the inside becomes less negative. It's starting to depolarize. Okay? So, right? So reception causes sodium channels to open. Sodium enters the cell crosses the membrane, enters the cell, and causes a depolarization of the membrane. Okay, causes a depolarization. That's important. Now that we've depolarized, it affects voltage gated sodium channels. Now these are sodium channels that are affected by the voltage. Okay, so when the cell is at rest, it's negative inside, it's positive outside, the sodium voltage gated sodium channels are closed. But when a small depolarization happens, it makes some of these voltage gated sodium channels open because there's been a change in the voltage across the membrane. So voltage gated sodium channels open, right? And that's these guys right here, okay? Voltage gated sodium channel, right? And when that happens, that small depolarization causes this voltage gated sodium channels to open, and this means that if we do that to enough voltage gated sodium channels, we'll get a lot of sodium coming in. Okay? So I've just drawn one here for simplicity, but you've got to imagine that a few channels of sodium channels open, lets a little bit of sodium in, depolarization opens more channels, more sodium comes in, and this opens more channels. Okay? So we could get a situation where we've got lots of sodium now inside the membrane, inside the cell. Okay? Remember, there was lots of sodium outside, not that much inside, so it's going to rush in. Okay? Down an electrical and chemical gradient. Remember, it was negative inside, so that's another thing that was causing more sodium to come in. Because sodium is positive, it's going to go towards towards negative regions, as well as towards areas of lower concentration. Okay? So, voltage-gated sodium channels open. Sodium moves into the cell along an electrical and chemical gradient. Okay? Now, what we had initially, when those few sodium ions came in, because these sodium gates open due to a stimulus, that's what you can call like a generator potential. Obviously. Okay? A generator potential, right? So you're kind of moving up away from the polarized resting state. Okay? Now, in most cases, you know, if you're not getting a proper stimulation, it won't cause a major depolarization. But if you reach minus 50 millivolts, if that depolarization reaches minus 50 millivolts, you'll have enough sodium channels open, enough voltage-gated sodium channels open to cause a massive influx of sodium ions. Okay? And when that happens, you get a massive entry of sodium ions into the cell. The inside becomes massively positive, and the outside becomes negative. So you've got a depolarization to the extent that we have an actual action potential. Okay, so sodium moves into the cell along electrical and chemical gradient. And this, if depolarization reaches plus 40 millivolts, this is known as an action potential. This is known as an action potential, and you will always get a proper action potential if you reach minus 50 millivolts depolarization. Okay, so for example, if we had a little bit of stimulation but it didn't get to -50, it will just go back down to the resting potential again. But then if we got a proper stimulation and it reached -50, then it would develop into an action potential. Okay? And that -50 is known as the threshold potential. If you don't reach that threshold, it won't develop into an action potential. If you do, it will develop into a full action potential. Okay, so now we've got lots of sodium in the cell, we've got lots of potassium still there, but what happens is, when you reach the action potential, a number of things happen. Or the main important thing happens is that potassium channels open. Okay, so the action potential causes potassium channels to open. So this is called the repolarization stage. Repolarization. Okay, so at this point, right at the top of the action potential, we've reached plus 40 millivolts. That's when potassium channels open. Now, this time, potassium will move out of these channels because not only is there a high concentration of sodium inside and a low concentration of, not only is there a high concentration of potassium inside and a low concentration of potassium outside, i.e. a chemical gradient, now there's also an electrical gradient. It's very positive inside and it's very negative outside. So there's essentially, you can think of it as two reasons for potassium to leave the cell. Okay? And now that those channels are open, potassium channels are open, potassium ions will move out of the cell. Okay, so repolarization. What I'll say is at the end of the action potential, I'll just mention here, under action potential, potassium gates open. Okay, so the potassium gates I'd like you to think of as opening at the end of the action potential. When those gates open, the repolarization is caused by potassium ions moving out along a chemical and electrical gradient. Okay? So potassium moves out along the chemical and electrical gradient, so out it goes. So out of the channels, out goes the potassium. And now there's lots of potassium outside and lots of sodium inside. It's the opposite situation of the resting potential. Okay? But because the potassium has gone out, now we get repolarization. Alright? So the outside, after the action potential, at this stage right there, you had both sodium and potassium inside the cell. So it was extremely positive in there. But now, because the potassium is going out, it's getting more and more negative again. Okay? In fact, so much potassium leaves at this point that it gets even more positive than when it was at the action potential. At the resting potential. Okay? More positive than even at the resting potential. Okay? So it's a kind of like it overshoots what it's supposed to do. Okay? So potassium moves out along chemical and electrical gradient. Overshoot, i.e. too much potassium goes out, overshoot causes a hyperpolarization. Okay? Which means that you don't just stop when you get to the resting potential, it goes even lower. Okay? Right? So, now we've got an opposite situation. Potassium is outside, sodium's inside. Okay? Now the ion channels close. Okay? So the potassium channels close again. Okay? Ion channels close. Ion channels close and the sodium-potassium pump restores the resting potential. Okay? Sodium-potassium pump restores resting potential. Is that on the board? Okay? Right. So, the sodium-potassium pump restores the resting potential simply by doing what it does. Okay? Remember, lots of potassium now outside, lots of sodium inside. What does the pump do? Remember, it transports 3 sodiums out, 2 potassium in. So, that's what it does. 3 sodiums out, 2 potassiums in, and in that way, the potassium that's outside moves back in, the sodium that's inside moves back out, and we are back. Okay? We are back. And that's that. That's the action potential. Look, how does it move along the neuron? Well, the action potential here, when the sodium came in, so let's just start again. Resting potential, fine. We get reception, sodium comes in, so we've opened this channel, so we've opened the voltage-gated sodium channel, for example, and we get lots of sodium coming in, okay? Now this sodium doesn't just stay there in this area. Because there's such a high concentration of it, it does what it normally would do. It starts to diffuse away from this area. Okay, we've got high concentration here, low concentration everywhere else. It starts to diffuse away. So we start to get sodium around here. Okay? And when that happens, the next voltage-gated sodium channel along will also experience the depolarization. So it opens, in comes the sodium. And again, the sodium doesn't just stay here, it diffuses away. And then the next voltage-gated sodium channel opens, and the sodium comes in, and the events of the action potential happen there. So I hope that makes sense, that when you start the depolarization in one end of the cell, the voltage-gated sodium channels open, allowing sodium in, it diffuses away, and other sodium channels experience that depolarization, causing them to open, causing the sodium to come in, causing the action potential. That sodium diffuses away within the cell and causes the next voltage-gated sodium channel to open, and thus the signal, the depolarization, and the action potential spreads along the whole length of the neuron. Okay? I think my final point is going to be this. Once a voltage-gated sodium channel has been opened by the depolarization and the action potential has happened here, it goes through a period called the refractory period, which is a length of time in which it cannot be stimulated, it cannot be opened. Okay? So, once the depolarization has happened here, this voltage-gated sodium channel is in its refractory period. Okay? Then the next one opens and it undergoes an action potential. Now, when this sodium comes back in, it diffuses in both directions. So in theory, you could get an action potential spreading in both directions, in theory. But what stops that from happening, and what means that the action potential only goes in one direction, is that because this voltage-gated sodium channel is undergoing its refractory period, it cannot be opened. So this voltage-gated sodium channel does experience the depolarization, but it can't respond to it because it's in its refractory period, so it stays closed. But this one, the next one along, that will open because it hasn't undergone a stimulation yet. Okay, so when this one has undergone its depolarization, it will also go through a refractory period where it won't be stimulated. So when the sodium comes in this voltage-gated sodium channel, the sodium will diffuse away again, but this one won't be activated. But in theory, if the neuron was extended and there was another voltage-gated sodium channel over there, that one would get stimulated. And so you make sure in that way that the signal only goes in one direction. After a certain time, they'll both return to normal and they will be able to be stimulated if the neuron was to be stimulated again. Okay? I think that's all I want to say about that. All right, if you have any questions, do email me or message me, that's fine. Good luck.